What homework?
That's homework.
What homework?
It's like review.
Oh, that'll be a review.
So
That's not homework.
And then there's also like a 15-point kind of stuff. That's not.
No.
So today is my last one. The stuff that's due today is the last stuff.
Unless,
That's what? Yeah. Oh, except for the actually part that's due Monday.
What if it's due Monday, but we make it worth your while?
how's it going to be worth my while?
We'll give you snacks.
Oh, something going on here.
How do you like your orange juice? With or without Coke? No, this is like the bribing. Seriously, with or without Coke?
Party up
I
Monday.
don't care.
Party up in the final.
I prefer Coke myself. No, just the chunks of drink. What if I bring you a big old can of horchata handmade by authentic women?
I don't know.
You were at the taco day, right?
Yeah.
Yeah, remember the horchata?
Oh, I didn't have any. Right. All right, let's take a look at integrals. And I will start off with the integral that we know from the single variable calculus. And I want to just write it like this, where I is an interval from A to B. And I think I've done this already, but today I want to try to make more sense of this and try to relate it to everything that we've been doing, this particular notation. And then I think we made a list of integrals of things over. So the idea behind an integral is that you're integrating a function over a geometric object. So the integrals is an integral of a function over a geometric object. And here's our example where the function is f, and then the geometric object is just a straight line interval. So this is our regular single integral that we've been doing since Calculus 1. All right, so from here we learned a few other integrals. We've learned some other single integrals where we integrated over a type of function. So when we're integrating a single integral of a function f, and just by convention, my little f would be a scalar function, and the big F would be a vector field. We're integrating over a curve C ds. And this is what we call the path integral. And then we did a double integral. Oh. Yeah, sorry. You guys taking notes in pencil? I need to make more room because I needed to include other stuff here. Sorry. Let's try that again. Okay. So here is that single integral of f dx. I need a little bit more room actually, because I'm going to write something else underneath it. This is our regular single integral. And then we have our double integral over a domain D. Sometimes we call it R for region, but domain D of f dA. So now the D's, by the way, have a lot to do with the geometric object that you're integrating over, right? So the dx, for example, here is the interval being partitioned. The dA over here is the region that's being partitioned. And then our third one is a triple integral over E of f dV. So these are the names we gave it. And these are the first two integrals that we did in this class, the double integral and the triple integral. Well, actually, we did some other integrals, but that's different. Okay, so now we don't often do this, but we've actually seen this a lot. Especially with the d theta. When we integrate from 0 to 2 pi of d theta, we're assuming that there's a 1 in there. And then you know that our answer is just 2 pi, right? Integral from 0 to 2 pi. We've done that in our heads a bunch of times. Yesterday I did one where I integrated with respect to x from -1 to 3 or something like that. And I don't know if you noticed that I just subtracted it. And so this integral over here is just, can you tell me what the geometric measurement of this answer to this integral is? Do you understand what I'm asking? Like if it was from a to b, integral from a to b, what's my answer going to be? b minus a, right? What is b minus a in terms of this I interval? It's the what? Lisa? The distance or the length. So, is that what you're going to say, Aaron? Yeah. It's the length of that interval. So the geometric measurement, I is a geometric object, and when I integrate this integral with 1 in it, it's giving me the geometric length of that interval. Now, that seems to be of no or little of no consequence, but if we take a look at this with a double and triple integral, we see something interesting. That if we take the double integral of d of f, where f is equal to 1, over your region D, remember what this is? Initially, this is like a volume of something, but it turns out that numerically, it is exactly the area of that geometric object. And it turns out that the triple integral, we've done this also, and I don't know if I've talked to you about this explicitly, but if in the triple integral your integrand is 1, you're essentially just looking for the volume of E. So there's some interesting geometry here with the integrals that follow along with the integrals. Okay? All right, now we're talking about new integrals where we're integrating over some other objects. Instead of integrating over an interval, we're integrating over a path now, a curve. And so we're calling this a path integral. And then we have a surface integral. integrate a double integral over s of a function, the capital S. And now, these things don't have arrows on top, so we're not talking about vectors. These are scalars, and this is a scalar. It's just a regular multiplication instead of a dot product in between those two things. And so, if we follow through the same kind of idea here, where we're going to do a path integral of the curve C of f, where f is equal to 1, ds, do you know what that might be? What is this equal to? So, kind of similar to this, the length of the curve. So, in other words, this is what we know of as the arc length. And if you remember the formula for the arc length, it was the magnitude of r prime dt, which is exactly what ds is. And so similarly here, when you integrate the surface integral, guess what this is going to be? Well, it's a two-dimensional, so it's the area of the surface area. So it's a surface area of that surface that we're looking at. Okay? All right. So these integrals, these 5 integrals, example integrals, are all taking in scalar functions, little f. And if your scalar function is equal to 1, then it directly measures the geometric object that you're integrating over. All right? So that's interesting geometry that we can do something with. Now, the last bit over here, we don't have a triple integral over some weird solid volume thing or anything like that, aside from our regular triple integral. So I think that's it for that. The only thing that would make sense here would be something that would be in 4th dimension that we're not going to talk about. So the last 2 integrals over here are kind of parallel to the single and double integral, but instead of a scalar function f, now we have a vector field over another geometric object, which is a curve again, and this time we have a dot product here. So when we do this, this is called a line integral. And then when we do the same thing except on a surface with a double integral, we call it a flux. So I think it's important for you to know your integrals. This doesn't even talk about how to compute them, but at least know what they are, so that when you're looking at an integral, you can kind of categorize or compartmentalize your brain into thinking, okay, this is a flux integral, so I know it's a flux integral, and then from there your brain should take you to the process of how to do a flux integral. Or if something looks like a path integral, this is a path integral, I'm going to go in this direction. Okay? All right. Now let's talk about the fundamental theorem of calculus. So this is our summary of integrals. Now let's summarize the fundamental theorem of calculus. And again, what I'll do is I'll start with the notation that we used in Calc 1 and then see if I can convince you that that notation kind of looks like some other notation. So in Calc 1, we see our first glance of the fundamental theorem of calculus. Technically, this is half of the fundamental theorem of calculus. And I'll write it like this. Instead of having little f dx, I'm going to have big F prime, because when they do little f, they write in the bottom that little f is equal to big F prime anyways. So I'm just going to go ahead and write it like this. And this, we know, is equal to f of b minus f of a. Instead of writing it like that, I'm going to rewrite it as f of x evaluated from a to b. And now if you stretch your ideas, your minds a little bit further, let me rewrite this again as, instead of the a to b, I'll write it as an interval, right? This is an integral of the derivative of f over this geometric object, which is an interval. And what I get is that it's the original function f of x, and then we're going to evaluate it. Well, it doesn't get evaluated over every value in the interval. It evaluates at the boundary of the interval, where this notation is the boundary. And if you look at the interval from a to b, the boundary is just a and b, right? The starting and the ending points. And a few ideas here that the order of A and B matters. So we have a specific direction. We're going from A to B, and that if you switch B and A, then you're going to get the negative of your answer, right? So is all that kind of starting to sound familiar, and how it might relate to, well, maybe it will. So we've had 4 major theorems in this one chapter. We'll start with the fundamental theorem of line integrals. So FUND, fundamental theorem. Oh, that's 1. Fundamental theorem of line integrals. Should I work on my handwriting? It's too late now. If you don't know my handwriting by now, you're in the wrong class. So, the fundamental theorem of line integrals is a line integral. Oh, yeah, it's a line integral. I hope so. It's called the fundamental theorem of line integrals. So anyways, the fundamental theorem of line integrals gives you a line integral. And the line integral, if you remember from the previous page, is an integral, a single integral over a curve of a vector field, right? A vector field. Now, a derivative of something, the gradient is a form of a derivative of something. And this happens to be a vector field. So the fundamental theorem of line integrals says that if you're going to take the integral of a vector field, right, a vector field that's a gradient of something, then it's essentially equal to that function evaluated at the endpoints of the curve. Endpoint of C minus F endpoint or start point of C. So suppose if I rewrite this as this, and f is a function of several variables, so my x here is not just f of x, it should be f of x with an arrow on top because it's a vector, evaluated at the boundary of C. The endpoints, starting and ending points. So the integral of a derivative of a function is equal to the original function evaluated at the boundary. Okay? I'll type that up at the end of all this because it's all going to be the same thing. It's the integral of a derivative of something is equal to the original function evaluated at the boundary. But the evaluation process gets a little bit different with different things. So let's take it up a dimension with Green's theorem. Green's theorem says that you're taking the integral now that partial of q over x partial minus partial of p over y. So that is essentially the curl of a two-dimensional vector field dotted with k. It turns out that we saw when we looked at Stokes that Green's theorem is just a special version of Stokes' theorem. It's just in two dimensions. So this is looking at a two-dimensional region D, and we're taking this double integral. So this is just a double integral, right? This is not a flux or anything like that. It's just a double, not a surface integral. This is happening flat on a two-dimensional plane. So that's one of the things that I want you to be able to do is when you're looking at an integral like this, there's two integral signs, and then it says dA. So two integral signs, dA, that's a double integral. It's not a surface integral, and it's not a flux integral, because surface integrals and flux integrals are a little bit different. So this is a double integral, flat on the xy plane, and then this becomes a line integral. Over C, well, let me erase C. Over, what's C? The boundary. It's the boundary of the region D. So instead of putting C, remember at some point they had C over there, and then I said, let's start calling this the boundary of D instead of just C. Because that's what we're doing, is we're breaking it down now. compare it again to the fundamental theorem of line integrals and the fundamental theorem of calculus. We have a double integral of a derivative of something over a region, over some geometric object. This is equal to its one less integral evaluated at the boundary of the original function. That's not the derivative anymore. See how that broke down to something? You're taking one integral less, you're integrating over a boundary now of the original function. This is a two-dimensional region, so D is the inside, and then the boundary of D is the outside. This should give you the same answer according to Green's theorem. Well, see, that's the thing, is that it depends on the problem. Most of the time, it turns out that the double integral is easier. It depends. It also depends on what's given. In fact, if we do these pictures over here, we have a curve, and then this is your boundary. And that's where you end up. So Green's theorem is essentially the fundamental theorem of calculus, except it's going from a double integral to a single integral. The fundamental theorem of line integrals goes from an integral to, this isn't quite an integral, but if we look at it as a zero integral instead of a single integral, it kind of just the same thing. You're evaluating at the endpoints. So these integrals you evaluate at the boundaries. And if we take a look at the last two theorems that we had, they're essentially saying the same thing. So let's see Stokes. So Stokes tells us that we have a double integral over a surface. So now this is a surface integral. Is it a surface integral? No, it's not. It's a flux, because the thing that we're integrating is a vector field. So it's a flux integral of a derivative of something. That's going to equal to one derivative less over a boundary of the surface of the original function, f. ds. So this is an integral evaluated at the boundary. One integral less of the original function evaluated at the boundary. And technically this is a closed circle, so we tend to put this circle around here for the flux to a line integral, a closed line integral. Well, the thing about Stokes' theorem is that the flux is asking you to take the flux of the curl. So if you don't have the flux of the curl, then you can't use Stokes' theorem anymore. But if it was the flux of the curl, then use Stokes. And usually your problem will say take the flux of the curl. And so automatically you should think about Stokes' theorem. So remember that this has to be an open surface, so that that open surface has a boundary. Because if the surface is not open, then you don't have a boundary, then that wouldn't make sense anymore. So the surface could be whatever the surface looks like, as long as it has an open boundary. This is your surface S, and then this is your boundary. And since we're talking about a flux and a line integral, the orientation is going to be important. Well, I think the orientation is going to go this way. Well, it kind of depends on the orientation of the surface. The orientation on the surface is going to going to control the orientation of the boundary. Is they just have to agree with each other. And then if we take a look at Green's theorem is usually written with a flux first, but I'm going to write it the other way first with a triple integral first. Or, sorry, I say Green's, I mean Gauss. Also known as the Divergence Theorem. No. So Stokes theorem, Gauss's theorem starts off with a triple integral, I'll start it off with a triple integral. And it's a triple integral of a derivative of something again. This time it's the div of f. And you're doing a triple integral, so our d is dv, and then this is a solid E. And this is going to, on the other side, we'll reduce one integral. So this will be a double integral. We'll take not the solid itself, but the boundary of the solid. So boundary of the solid, which is a closed surface, it turns out. And the antiderivative, so to speak. So the div of f, so we're going to take the original f. And now since this is a vector field over a surface, we have to look at this as a flux integral. This is a flux integral over ds, or over the boundary of E. And a minor addition here that we don't normally, the book doesn't do, but because this is a closed surface, a flux integral over a closed surface, we tend to have this positive orientation business like we did with a line integral. Triple integral is just called a triple integral. We didn't have any fancy names for that. Well, there's no triple integrals over vector fields, and there's no triple integrals over parameterized solids or anything like that. So we didn't define anything like that here. They exist in math, but it's not useful in physics and engineering, so really only math people play with that. But the point here is that when we're taking an integral of a derivative of something, it's going to put it down one integral less, and then we're taking the original function over the boundary of that object. So that's really the idea behind the fundamental theorem of calculus. And with that idea of the fundamental theorem of calculus, all these things that we were just looking at, the Gauss, Stokes, Green's, and the fundamental theorem of line integral, are all some variation of the fundamental theorem of calculus. So if we were to sum this up, probably say the integral of a derivative of a function over an object let's put an object, we know it's a geometric object, is equal to the, say, one less integral of the original function. Yeah, and when we say zero integral, we just evaluate at the endpoints. Over the boundary of the object. And when I say endpoints back in Calc 1, it's evaluated at the endpoints. It's really the boundary of that interval, right, from A to B. So in math, they have these things called manifolds and functions, differentials. And so in math, in math, when you look at double and triple integrals and whatever quadruple and quintuple integrals, it all is generally the same idea, and so you can put it together into one kind of unifying statement. If you take an integral of a derivative of something, and omega would be your differential that we're talking about, over some sort of geometric manifold, then this is equal to one less integral, but the one less integral would be understood here, and then this becomes the fundamental theorem of calculus in general in math. So this would be a really cool tattoo to have. What I would suggest is just you get this tattoo, and then somewhere along the line you'll get the meaning of this, and then it'll be internalized, and then this will be the most fabulous thing in math ever. Anyways. What? I was going to get a tattoo of the integral sign, just the integral sign, on the side of my leg. I don't know. Maybe one of these days. Yeah, but this would be a cool tattoo to have, like in your shoulder or
Lower back.
without the box. The box is lame. Let's take the box out. Anyways, if you're looking for a tattoo, bam, there you go. Do it. Okay, so I usually give this problem as extra credit, but I ended up giving you a different extra credit problem. So it's too much. I know it's never enough, but that's the thing, is that it's never enough. I give you more, and you're going to want some more. It's like a drug. An extra credit drug. Once you do extra credit, you never go back? I'm looking for something I should have had prepared, but I didn't.
Thing for the final. Are you going to make that one for the final?
Oh, did I make it already?
Oh, they had a take-home final? What? And you don't get take-home final?
You want?
11. What?
Do you seriously want to take home final?
No, because you're going to make it really hard.
Because I can give you take home final if you want. Oh, this is Mathematica printout. No. anyways, I had this cool let's take a look at this rocket problem. So this is problem number 6 from a take-home final, and this is, as we do this, you'll see that you should be happy that you're not getting a take-home final. All right. So it says, consider the surface S of a rocket given by the union of all these surfaces. So imagine putting these surfaces together. We have a top cone. So this is a cone. It looks like it has a negative with a square root, so it should be an upside-down cone. It's an upside-down cone that's moved up 10 units. All right? So the tip of it should be at 10. And you can use a graphing program to draw this out if you want. And then the second one is a washer. So let me just sketch it out a little bit. So this is the top part. It's an upside down cone. The second one is a washer. It looks like it has it goes from 1 to 2. So that would be at z is equal to 6. So it's basically a disk with a hole in it. The next one is a cylinder. Radius 1 going from 0 to 6. Oh, that's it. There's only 3. I used to have one with like 5. Oh, I think the one I had was a flashlight. It was a hemisphere, a sphere, a cone that's cut up, and then another cylinder or hemisphere. Yeah. Oh, lots of fun. All right. So if you put these things together, it turns out that you're going to get this thing that might look like a rocket. I was going to try to piece it together, but let me put it together here. So this looks like this is more or less how your combination of all these would look like. So part A says to give a parameterization for each of them. Make sure you include the limits for your domain. So we could do parameterization. Let's just pick one. I don't want to do all of them. Let's parameterize. What do you guys want to parameterize? The cone, the disk, or the washer, or the cylinder? Let's do the cone. All right, let's do the cone. S1. Turns out that there's going to be a couple ways of there's an infinite number of ways to parameterize this. I'm going to parameterize it a couple of ways just for fun. We'll call the first one the graph parameterization, where your parameterization R of xy, and since I'm calling it a graph parameterization, I tend to use the original variables. So I'll use x and y. And then x is x, y is y. That's what makes it nice. And then the z is just whatever the z is. 10 minus 2 square root of x squared plus y squared. So that seems like an easy parameterization. But what you have to do is be careful about your domain. You want to include the limits for your domain. So I have to try to describe the limits now for my x and y. And so if I know that they're going to be constants, I probably want to set it up like this. But is it really going to be constants? So what looks like it's going to happen is that this cone, I needed to put limits here for the cone. 6 to 10, sorry. I needed to put limits there because I need to stop the cone somewhere. Otherwise, technically it'll keep going on forever. So the limits for the cone is from 6 to 10. That's my z values. So in terms of describing my x and y values, what I need to do is I need to look at this on the xy plane and see the shadow that this is going to make. And the shadow that it's going to make, it looks like, if I'm just looking at this right here on the xy plane, the shadow it's going to make is a circle. And so that's going to be hard to describe using x's and y's. So maybe I'll just describe it a little bit differently. Your domain is going to be a circle radius. What's the radius? So at 10, it's at the tip. So the width of this thing, wherever it ends up over here, is going to be basically the intersection of the z's equal to 6 plane. So if I set this whole thing equal to 6, that might give me my circle. So 6 equals 10 minus 2 square root of x squared plus y squared. So I take this over, I get, is that 4? Divide by 2, and that's 2. Square root of x squared plus y squared. So that's just radius 2, right? Is that right? So this will have a shadow with radius 2. So in terms of finding my parameterization, this is one way to parameterize it using the graph parameterization. Now we could parameterize this a little bit better if we want to. If we decide that we want to parameterize this using constant limits. We could also parameterize using cylindrical or polar coordinates. So if you were doing this test, I'd probably just do one of these. If I want to see it using a graphing program, I probably want to do this parameterization because I'm going to have constant limits here. But if I want to try to do some computations with it, I'll probably use a graph parameterization because it'll end up being a little bit easier. So the cylindrical coordinates tells me my x is r cosine theta and my y is r sine theta. But my z is equal to z, and z is equal to 10 minus 2 square root of x squared plus y squared. So if I just put x squared plus y squared is equal to r squared up there, then this is what my z is going to look like. So this is another parameterization for that same surface, but this time my limits will be constants. Okay? All right, so now I can put this in my graphing program and get that actual one part of my surface. So the other parts of the surface are whatever the other parts of the surface. Let's focus on trying to do C and D now. Take-home test? All right. So G is equal to this vector field, and they want us to compute the flux of the curl. Flux of the curl. What do you think of? We're going to use Stokes. Okay, flux of the curl. The surface S with an outward orientation. Now, this is an open surface. This is an open surface, right? And the surface is open here on the xy plane. So really, if we take a look at just the xy plane, this is what we're looking at, right? This is the boundary. So this is the surface S. This is the boundary of S. In fact, maybe we could take a look at that. Just as a circle in the xy plane. Now let's figure out the orientation, because we're supposed to have an outward orientation, outward orientation. I guess the only thing that really matters is the cylinder. If you're on the cylinder with an outward orientation, which way is this circle going? Not downward. It's not a, I'm just talking about the curve part. Which way should this go? Clockwise? Clockwise from the top? Counterclockwise? So look at it. If you're trying to draw the orientation with your right hand, the thumb sticking out this way, outward orientation, you're going to push your boundary to go from, let's say, the positive x to the positive y-axis, right? So it's going to go in this direction. All right, so if you're looking for the flux of the curl, the flux of the curl of G, according to Stokes, you just look at the boundary. It becomes a line integral over the boundary of S of the original function G. Dotted with ds. Right? So let's give get a parameterization for this. This is it looks like it's in 2D, but technically it's a 3D curve. And so 3D curve means that we can, it's a curve, so it's just one parameter t. And what would be a good parameterization for this? So the radius is what? The radius is 1, so cosine theta, sine theta. Oh, there's a z component. What's z equal to? 0. Why is it equal to 0? Because it's on the xy plane, and z is equal to 0 on the xy plane. What would be your what? Your ds would be the derivative of this. So your ds, remember, is the derivative of r, your parameterization. So we need the derivative of this, which is negative sine t. Oh, I put theta, sorry, t. Cosine t, and it's 0. And what happens when you dot it with 0, well, you're going to dot it with this horrible looking, well, it turns out that the z is the only horrible part, right? And so you're just going to dot it with this. So G, and before you dot it, you want to put the r of t in there. It's going to be y is sine. This is y, right? And z. So y, oh, z is equal to 0. So the first one is going to be sine t times 0. That's going to make that disappear. The second one is going to be cosine, sine squared. Sine squared t. And the last one is going to be something, but I'm not going to care because when I dot it with r prime, it's going to be 0. So it turns out that this is also 0. So when we dot this, g r of t dotted with r prime of t is going to equal to just sine squared t times cosine t. And on this single integral, this line integral now is going to become a single integral. It's going to be an integral from 0 to 2 pi, because that's our limits for t, of sine squared t times cosine t dt. And this is an integral that you can do. It looks like it's a simple u substitution. Let u equal a sine t, and then the cosines will cancel. And then you don't even need Wolfram alpha for this. I expect you to be able to do these types of integrals on the exam without Wolfram alpha. Say it again? It doesn't matter. Technically, it should be t, because yeah, t or x. Mostly our single integrals will become t integrals, because that's what we're used to. But really, you can call it whatever you want. You can call it s, you can call it theta. All right. Now the last one we don't have time to do, but let's imagine what will happen here. We can, well, who knows? We might be able to do this. Here it says to compute the flux of F. So we want flux of F over the surface. Now the surface is open, so we can't really use Gauss's theorem unless we close it. So what we can do is we can close it, close S with, they call it S1. Let's close S with S1. So now it's a closed surface. Now we can use Gauss. We're going to add another surface to this. So we're going to close S with S1 by adding a disk. Simplest type of surface that you can put in the bottom, x squared plus y squared is less than or equal to 1 when z is equal to 0. So that disk will close it. Well, though previously we used a circle, so that's not a disk. Disk is like filled in circle. So now this is a filled in circle. So if we close this, now we have a closed circle. Now we can use Gauss, but we have to make sure we close it up. So if we add on this other flux integral, S1, then we can use Gauss. So this is what we're looking for. And so we have to do a couple of computations. Now this looks like it's going to be hard, the triple integral over 3 things, right? Let's take a look at this again carefully. Let's take the div. So the div of this, the derivative of the first component with respect to x, 0. The derivative of the second component with respect to y, 0. Derivative of the third component with respect to z, 5. We've got a constant. So let me show you how easy this integral now will be. E is a solid that's enclosed by all of these shapes. 5 dv. All right, let me rewrite that. Let's take the 5 out. What is this integral equal to? It's the volume. 5 times the volume of your solid, right? What's your solid? Your solid is a cone in a cylinder. I think I can find the volume of a cone in a cylinder, right? So the cylinder goes from 0 to 6 and has width or has radius 1. The cone goes from 6 to 10, so it has a height of 4, and then the radius, I don't know if you guys remember the radius, but the radius turned out to be 2. The small radius is 1, the big radius is 2. So the radius for the cone is 2. So whatever the formula is for the volume of a cone, where your height is equal to 4 and your radius is 2, and the volume of the cylinder where your height is equal to 6 and your radius is 1, then you're just looking for some geometry problems. Okay? Cone, height 4, radius 2. Plus volume of cylinder height 6, radius 1. Okay? Now, my flux integrals here should be double, but it doesn't really matter because you should understand that this is a surface, not a line. So the flux integral, so now the only other thing to find is this. Is this going to be hard or easy? S1 is a flat two-dimensional disk. So I can easily parameterize that with x and y and 0, where x and y is a circle. I guess formally it's a disk, radius 1. So the z component's equal to 0, and if you punch that information into here, you'll see that it'll turn out to be easy, or it actually might turn out to be 0 because I'm looking at the, maybe not. But in any case, I think it'll be an easier integral to deal with that you should be able to handle. But this looks like it was a tough one, but it turned out to be just a problem in finding volumes. Okay? So now we're able to tie in all these differential, all the fundamental theorem of calculus, all the 3 different calculus, and then we tied that into our different types of integrals. And then knowing that if your integrand is 1 for certain integrals, it's just a geometric measurement of an object. Okay? All right. So your exam will be one problem. It's a projectile problem. Since I thought I wrote it out, but Chris wrote it on the board. Somebody took a picture of it, and then I forgot to put it online. So problem number 1 will be a projectile problem. Problem number 2 will be an optimization problem. Problems number 3, 4, 5, 6, and 7 will be on the fundamental theorem of calculus, aka chapter 16 stuff. Okay, so tomorrow we'll take a look at some problems from chapter 16 and any other problems that you guys might want to go over as I review. All right, see you guys.